let's talk about change of phase and latent heat as well. So right now on the textbook, I would like you to read page 120 to the next page right here. Pause the video and we'll talk about the key concept later on. Okay, so first of all, as I expect you have studied in IGCSE, then phase change is a very simple concept where the states from solid, liquid, and gas they will interchange from one to another. We have names for them, including melting, freezing, vaporization or boiling, and condensation, going from one state to another. And you should know that the energy for melting and freezing is basically the same because you are more like creating the bond or breaking the bond, the same kind of bonding. And same for vaporization and condensation. Again, these two will be the same. So if you talk about latent heat later on, the latent heat of melting and latent heat of freezing of the same material will be the same, and the latent heat of vaporization or the latent heat of the condensation of the same material would surely be the same as well. Okay, so on the next page, it basically tells you some more ideas about the latent heat in a more microscopic view. That means in the particle view, it actually means that when you try to increase the separation for the molecules, that means, for example, you change from solid to liquid or liquid to gas, then you are like increasing the separation between the particles. In fact, you can also change from solid to gas directly. Those will be a more special case when you change to solid to gas, and not quite often. One example would simply be CO2. The solid of CO2 is the dry ice that you should have probably seen it before when you try to see something that is really cold in the supermarket maybe. Or some ice cream store they use CO2, or some kind of cake they use CO2 too, which is dry ice to for storage. And you will see those smoke, they can then simply be coming out, and we call the process, if you try to Google it, then you can see the name sublimation. And then of course for the photo, then you could see something like this. I'm pretty sure that you have seen something like that before, and very cool effect that you can see. So changing from solid, which is dry ice, to CO2 directly. Be careful, the CO2, if you have too high concentration, it will not be good for your health also. So back to the textbook here. Basically, the main concept that we need to know is what you learn in IGCSE, so the calculation of specific latent heat. Depending on what you are referring, so like I said, there could be different cases depending where you are melting or you are boiling, etc. Talking about the equation, we are now using Q instead of E, and then L is representing the latent heat. So let's quickly talk about the unit of latent heat. Since you know the unit of energy is joule, and so the units of M and L separately will be kg, and then you will want to know the unit of latent heat, right? And so the unit of latent heat will simply be, if you try to rearrange it, joule per kg. Okay, so that simply is the definition. Also, you may say, for example, it could be how many joule per unit mass, which is kg, for going through a certain change of state. So it could be fusion means going from liquid to solid in that case. Okay, and here is a table of different kind of substances and their own latent heat, and you can see there are certain patterns. So right now, the first thing I would like you to do is, can you observe, you may want to pause the video, can you observe there's any pattern on the table right now? Pause the video and I'll get back to you. Okay, the first pattern you will surely find out, of course, is the temperature of melting and temperature of boiling. Surely boiling must be higher than the one that is melting, because this is simply the state on how we talk about the particles, how separate they are. Of course, boiling means changing to this gas state is the furthest apart from each other. So therefore, the temperature must be the highest also. So this one isn't really that interesting, and I think it's very obvious. But the other thing that you may find out is the value of latent heat of vaporization or boiling. The numbers of a respective substance must be higher than the specific latent heat of fusion as well. If you try to compare for water, is 2000 something versus 300 something, or for example, copper is 2600 versus 200. The other thing that I would like you to do is I have already copied the table just now to your question set, and I would like you to go online and search for an extra information, and I will want you to copy, write down the numbers here, which is the thermal conductivity of each material. So try to give them a number over here. Afterwards, what I want you to do is try to observe if you can see any pattern between the thermal conductivity of each material and the other data simply. So pause the video now and try to do it first. Okay, so it took me about 2 minutes to search on Google and try to find from different sources on the thermal conductivity. So first of all, I will want you may want to double check mine with yours in terms of the number, but of course, because of different sources, it may be different. What I would say is what you need to ensure first is the unit, because there are actually different kind of unit. For example, even if we don't talk about thermal conductivity, for length, there are something called metric system and empirical system also, like mile and meter. So figuring out they are in the same unit is quite important. Here, what we will prefer, if you do the same, then we would like to use the unit which is watts per meter per K, which is Kelvin. So I hope you can see that thermal conductivity, even in terms of the units, is different from the latent heat. And even if you try to think about specific heat capacity, it is also different, because if you think about water, it is 4200, while for these kind of metal is a few hundred. So you can see they are simply different thing, and they in fact, if you try to say find any pattern, I would actually say the only pattern that you may find is the first two, which is water and ethanol. They have a very low thermal conductivity. That means they cannot actually conduct heat quite quickly. While for the metal, because of their state solid, they can actually conduct the heat, and especially if they are metal which has the free mobile electron, and therefore they are very good conductor. In that case, their thermal conductivity in terms of the number is relatively higher than the liquid itself. So you may ask, so how come we will get burned by water, like hot water, so easily? And that is something to do with because the water, when probably you got poured, then it is running water, so kind of flowing through your skin. So in that case, it will be a different idea of conductivity. At the same time, water has a high specific heat capacity. That's why they can release a lot of energy at once. While the metal, even if you touch it, actually, you also get burned by touching metal also, but then metal in theory will cool down quicker. Okay. One more interesting thing that you may want to see is among all four of metal here, there was a video that you may have seen in IGCSE, but I'm going to show you again, which is an experiment to check qualitatively on each metal. So according to our number here, you should find the copper has the highest thermal conductivity, followed by, so I put 1 here, followed by who? Followed by aluminium, and then iron, and then lead. Okay, so here I got a video which I actually have iron, aluminum, copper. Okay, so let's see if the sequence is right. So what they do is they put this setup which has the same length, and so they heat in the middle and see which one will have the, I think this is the wet or butter, I think it's wet, would drop down first. So from the time, then you can basically deduce which one has the highest conductivity and the lowest. So I think at the end, let's see, there is sequence. So we have aluminum go first, and so aluminum actually should have the highest conductivity. So how come I will find 385? I will want to double check that again. And then iron actually is the second, and then copper is actually the third. So actually this is all messed up. That is very strange. So let me take a look again.
A few moments later.
Okay, so what I understand why my data is different from the result in this YouTube video now. So the reason, well, first of all, when I try to think about why, I was thinking maybe, just maybe, the specific heat capacity would also matter for these four metal. So what I do is I also go online, Google, the values of all these things. So I find out these are the number. Apparently we have the lowest being lead, followed by copper, and then iron, and aluminum is the highest. And after that, if I try to compare with the result, it still doesn't make sense because aluminum is having the highest specific heat capacity. So there's no way that it would be, I mean, while copper, you can see here, copper is having 386. So copper should have a higher temperature, given that they have the same energy. But then copper should have the highest thermal conductivity. So no matter what, copper should be the fastest one, right, in this experiment. But copper is somehow at the fifth. So that is an issue. I find out very strangely. And eventually I managed to look up the comment section, and I just find out people are also complaining about the accuracy of the experiment. And I think maybe they just didn't hit up the rod at the very good position. Maybe it's a bit off, maybe. And I try to look up some other experiment, and I can put the link in the description. And so at the end, you will find out like this one, copper will go off first, aluminum, brass, and then steel. So basically this would coincide with our result where copper should be the highest conductivity, followed by aluminum, and then maybe iron afterwards. Okay, so I think this is a big lesson for us to learn, including myself. And I knew this video for long, and I just realized this video actually, I mean, the experiment itself is actually not reliable. So yeah, really interesting to see that. So I think this is a very interesting thing. You may want to take a look. Although it may not be sufficient or suitable for you to do IA, but definitely I think this is something we could learn in the nature of science. Okay, so you may ask me, so what kind of observation that you should have? Again, my answer is there actually isn't any very straightforward pattern. The atomic structure of each metal are quite special, so you can't say they have whatever linear or certain trend that you can tell directly. I would rather say, if you like, you can try to do a statistic. As far as I know, there isn't a really clear trend, except for maybe, like I said, for solid and liquid. Of course there will be a clear difference because of the basic structure of the particle model itself. The separation between the atoms are so different, so that will make a huge difference in terms of the conductivity. But other than that, I would say actually the answer is actually no specific pattern. I wanted to ask you to do the next two example, but I want to keep this video short, so you may want to do it now, and I'll explain in the next video.